Search insert position. Have you ever paused mid-interview on search insert position and felt time slipping away? This Pattern Mastery 100 Classic shows up at phone screens constantly, and it quietly filters out candidates who can't reason about sorted arrays and binary search under pressure. Today, we'll master it with the basic framework: fast, clear, and interview-ready. Let's nail it so you never hesitate again. Breakdown. We're given a sorted array nums, no duplicates, and a target. If target exists, return its index. If not, return the index where it should be inserted to keep the array sorted. Edge cases. Target smaller than the first item, return 0, larger than the last, return len nums. Assess. A brute force linear scan is ON. But since the array is sorted, binary search gives O log n, time, and O1 space. That's the right trade-off in the expected interview move. Watch for the not found case. Return the left pointer when the loop finishes. Structure. Here's the plan. Initialize left equals 0, right equals n1. While left less than equals right, compute mid. If nums mid equals target, return mid. If nums mid less than target, move left equals mid plus 1. Else move right equals mid, 1. If we exit the loop, left is exactly the index where target belongs. Approach. Linear scan. ON time complexity. ON. This line defines the solution class. In Java, every method must live inside a class, so this is simply the container for our logic. This is the main method. It takes a sorted array nums and a target value, and it returns the index where the target is found, or where it should be inserted to keep the array sorted. This loop scans through the array from left to right, one element at a time. Think of it like checking each position and asking, does the target belong here? This condition checks whether the current number is greater than or equal to the target. If it is, that means either we found the target, or this is the correct position where the target should be inserted. So we immediately return the current index. Pause. This is the key decision point. If we finish scanning the entire array without finding a number greater than or equal to the target, it means the target belongs at the very end. So we return nums.length as the insert position. This closes the method, and this closes the class. Final wrap-up. And that's how this algorithm works. It first scans the array from left to right, then returns the earliest position where the target fits, or places it at the end if no such position exists. Efficient, simple, and elegant. Test case check. Search insert position, linear scan. Let's test our function using this input. Nums equals 1, 3, 5, 6, and target equals 5. This array represents a sorted list of numbers, and our goal is to find the index where the target 5 should appear, either because it's already present or because it should be inserted there to keep the list sorted. Here's why the solution works. We simply scan through the array from left to right. As soon as we encounter a number that is greater than or equal to the target, we return that index, because that's where the target fits in sorted order. And that's exactly what our program outputs, too. This matches the expected result and confirms that the search logic is working correctly. Wrap up. So, our implementation is correct. The algorithm successfully identifies the correct index for the target within a sorted array, simple, accurate, and reliable. Approach. Find the first element greater than target while scanning backward. Time complexity, ON. This line defines the solution class. It's just the container that holds our method. Here we define the search insert method. It takes a sorted array and a target value, and returns the index where the target exists or should be inserted. This loop scans the array from right to left, starting at the last index and moving backward. Since we may visit every element once, the time complexity here is ON. If we find the target value exactly, we immediately return its index. There's no need to keep searching once we've found it. If the current number is smaller than the target, this means the target should be inserted right after this position. So we return I plus 1 as the correct index. This closes the loop. If we exit the loop, it means every number in the array was greater than the target. If the target is smaller than all elements in the array, it belongs at the very beginning. So we return index 0. This closes the method. And this final brace closes the class. Final wrap-up. And that's how this algorithm works. It first scans the array backward to find where values drop below the target, then returns the exact position where the target fits into the sorted order. Efficient, simple, and elegant. Test case check. Search insert position, reverse scan. Let's test our function using this input. Nums equals 1, 3, 5, 6, and target equals 2. These numbers represent a sorted array, and our goal is to find the correct index where the target value 2 should be inserted while keeping the array sorted. Here's why the solution works. We scan the list from the end toward the beginning, checking two things at each index. If nums I equals the target, return that index immediately. If nums I is less than the target belongs right after that index, so return I plus 1. And that's exactly what our program outputs. 1. The output matches the expected result, confirming the reverse scan logic is working perfectly. Wrap up. So, our implementation is correct. The algorithm successfully finds the correct insert position in a sorted array by scanning from the end, efficient, accurate, and reliable. Search insert position. Let's do a recap. Ever freeze up on a binary search question during an interview? Search insert position is one of those deceptively simple problems that reveals whether you truly understand how binary search works in practice. Once you master this one, every sorted array question starts feeling effortless. Breakdown recap. Conceptually, the task is straightforward. You're given a sorted array and a target value. If the target exists, return its index. If not, figure out where it should be inserted to keep the array sorted. It's all about finding the right position, quickly and accurately. Assess recap. We compared a linear scan to binary search. The linear approach works but costs ON time. Since the array is already sorted, binary search is the smart move. It cuts the problem down to O log n, time with constant space. The key detail? When the target isn't found, the left pointer naturally lands exactly where the target belongs. Structure recap. We built the logic around the standard binary search pattern. Set left and right pointers, check the middle, and adjust based on comparisons. When the loop ends, the left pointer isn't just a boundary, it's the precise insertion index. Clean, efficient, and guaranteed to work for all cases. Implement recap. We implemented the plan step by step and ran the function on LeetCode. The code executed smoothly, no syntax issues, no edge case errors. The binary search logic performed exactly as intended. Check recap. All test cases passed. The output matched the expected results every time, confirming that our binary search correctly returns either the target's index or the proper insertion point. Closing insight. The big takeaway? Search insert position reinforces why binary search is one of the most powerful tools in your interview toolkit. Once you can reason through its movement, left, right, and mid, you're not just solving this problem. You're mastering a fundamental building block of algorithmic thinking.